Okay, so let's work through the warm-up together. It says, without using a calculator, determine which of the following numeric expressions are equal to 1/4 with a base of 4 and a power of -5. Okay, we did this for a reason, because we really want to start stressing that you need to not use a calculator all the time, because we know some rules of exponents, and if you don't, you need to get better at them, because this is something that's going to be expected that you know on the SAT. Okay, I know that we don't teach to the test, but it's something that you're going to need to know. This is something that very well could be on the non-calculator portion of the SAT, being able to identify which one is equivalent. Okay, so when we talk about this one, what does a negative exponent mean? Anytime we have anything that's a negative exponent, what happens to the base? Yeah, it's a reciprocal. It flips to the opposite position. So right now it's in the numerator over 1, and it flips to that opposite position in the denominator. So technically, when we rewrite this, get it better. There you go. When we rewrite this, it's 1/4 with a base of 1/4 all the 5th power. When you rewrite it to have no negative exponent. When you guys have negative exponents, we would recommend that you rewrite it so that you actually know what's going on. That's going to be very beneficial today when we're talking about growth and decay. Okay, so whenever you see negative exponents, I want you to right away remember you have to take the reciprocal, okay, and flip the fraction. All right, so that one is what it means there. So let's talk about all of these here. What does this one become when we rewrite it? What's the base now? Yeah, 1/4. So again, whenever you see an exponent with a negative, all you do is you flip it, and then now that exponent becomes positive. Okay, and that's what we just did, right? Nope, we didn't do that yet. Okay. When we're comparing the two, when we look at the original and we look at this one, we want this to be like this. This will be the best way to do it, with the same exact bases. We want to have the same base. So when we look here, how do we get this 4 to be the same base? How do I get this to be 1/4 too? Well, yeah, technically, yes, but how would I make this 1/4 using exponents? What did we just talk about? How would I make that 1/4? Yeah, I can make it negative. So this can become 1/4 to the -1 power. Again, manipulating it so that you can rewrite it with the same base. I like to work with positive numbers, and that's why I rewrote it with the 1/4 as the base. Okay, so then I have 1/4 to the 7th power. Now that you have the same base, you are allowed to use rules of exponents, which means that you add the exponents because I have the same base. So when I add them, what do I get? 6. So technically now I have 1/4 all of the 6th power. Well, look at here. What is this? What is the power when I add these together? 6. So this one works out. Okay, so manipulating it in a way to get the same base. You want to have the same base so that you can figure out if it's equivalent or not. All right, let's look at this next one. What happens again because I have this negative in the exponent? What happens to the base? Yeah, it becomes a 4. So now it's 4 to the 6th. That's not 1/4 to the 6th, so this one's gone. There's no way that one can be it. All right, let's look at this next one. We kind of already talked about this, right? 1/4 to the 6th power. Is that going to be equivalent to our original expression? Yes, because technically, I'm going to write this out too. Technically, you can rewrite this as 1/4 to the 6th because you're adding exponents. So yeah, that one works. Again, using those rules of exponents. I know that you only spent about a week or two in math 2 with rules of exponents, but you need to start getting a little bit better and more efficient with rules of exponents. Adding them when they're multiplied together, subtracting them when they're dividing. The negative means that you're flipping the fraction. Something that you can automatically just do in your head, because it's not really that difficult, it's just knowing those rules. Okay? So now let's look at this next one. Here, what does this become? What's the base? 1/4. Again, we're going to keep doing the same thing over and over again, I think, because we really need it. Well, is 1/4 the 6 just like our original one? Yes, so that one works. All right, this one's a little strange. You know, you're looking at this, you're like, how the heck am I going to do this problem? You can rewrite them in ways that have the same base. What is a way that I can write 16 with a base of 4? 4 to what power gets me 16? Squared. So technically I can rewrite this as 4 squared to the 1/4 and 8. However, they're still not the same base. So what would I have to add to this exponent to make it the 1/4? A negative. Very good. So now I can have 1/4 to the -2 and 1/4 to the 8. And again, we really wanted to give you this warm up so that we got used to not always relying on the calculator, because you're not going to have that when it comes to the SAT. This is a very common one that they're going to have there. Now, when we add our exponents, what do you get? Yeah, 1/4 to the 6, and that's our original, so we're good. Okay, so manipulating it in a way to have the same base so that you can evaluate if it's equivalent or not. All right, looking at this next one. This one has the 1/4 base, so we're good. However, again, this 16 is kind of an issue. We need to have the same base, but how can I rewrite 16 as a base of 4? How can I rewrite 16 with a base of 4? 4 to the what power? Yeah, 4 squared. Okay, so I have 1/4 squared. Okay, I'm just rewriting all this out just so that you get used to what I mean by when I say that. Obviously, you don't have to rewrite it like this every single time. But it's still kind of weird here. We technically can just rewrite this as 1/4 all squared. Because technically 1/4 times 1/4 is 1/16. And then I have 1/4 to the -4. And when I add the exponents, what do I get? Yeah, -2. And that one does not work, because our goal is to get 1/4 the base of 6. Sorry, the base of 1/4, the exponent being 6. Okay, so yeah, that's probably a little challenging, a little confusing, but we're going to get better at it. We're going to do a little bit more practice with that today, but we're going to try to stay away from the calculator for a little bit. Okay? Do you have questions on any part of that? The biggest things, again, you can always rewrite something, hopefully, with the same base. Not all the time, but most of the time. And then you have to make sure that you know those exponent rules. When you multiply them, you add them together, the exponents. When you divide, you subtract them. When there's a negative, you flip the fraction. Okay, those are the big ones. I mean, there's more, but those are the big ones. All right, so go ahead and take your notes out. It's a pretty short day. If you like highlighters, today would be a good one to have highlighters. We do have highlighters available to you if you need them. But I like, maybe if you have an orange one and someone has a yellow one, then you could switch during the notes, because I'm going to be using 2 different color highlighters today. So if that's something that interests you, because you're a visual learner, then definitely have those highlighters out, okay? Because we will be working with some stuff that we really haven't done before. You have done exponential growth and decay, though, in physical science, if you took physical science, so, or chemistry. All right. So, what's cool about exponential growth and decay, when you ever hear the word in English, exponential, that means it's just growing really fast. So if you ever put maybe a good word for your English vocab when you're writing an essay, if you're talking about something rapidly growing, that's exponential. Or rapidly decaying, that's exponential as well. So yeah, something fell. Are you okay? Yeah. Thanks. She's not here. She's been gone for a while. What is this? Oh, that's weird. All right, so the simplest type of exponential growth function has the form of y equals b to the x power. So my exponential growth function, that was supposed to be a highlighter. My exponential growth function is when b is greater than 1, which is our base. So when our base is greater than 1, so 2, 1.5, 1.1, 1.01, it's going to be called growth. On the other hand, when we have decay, we have to be in between 0 and 1. What we learned yesterday is that the base can't be less than 0. or 0. Okay, otherwise you're not growing. It wouldn't make sense. If you just get a function y equals 0, that's not growth. It's just a one linear line, y equals 0. Okay, so that's why we have to be between 0 and 1. So now let's talk about this. Without graphing, determine whether the function represents growth or decay. So let's take a look at this one. Is the 3 or the 2/3 my base? The 2/3. I'm going to highlight this. Is 2/3 greater than 1 or between 0 and 1? Between 0 and 1. So I'm just going to write this out again for the sake of notes so that you don't forget. It's between 0 and 1, which means we are in decay. We're going to be going down rapidly. Questions on that? Let's look at this next one. There's really nothing we can do here, so always look and check that exponent and see if there's a negative or if there's something that we can rewrite. In this case, we can't, but we have 4/3, and you ask yourself, is that greater than 1 or between 0 and 1? 4/3. It's greater than 1. So 4/3 is greater than 1. I know that because the 4 is bigger than the 3, which means I have growth. Oopsies. Growth. Yeah, so if the number is bigger on the top than it is in the denominator, then it's greater than 1 for sure. Yeah. What? Well, yeah, now you know something. Oh, yeah, I taught you something, right? Okay, so now we look at this one. You could probably be like, oh, it's growth. We've got 2 here. However, there is this thing called a negative exponent, which means that there's something happens. When I have a negative exponent, what happens to the fraction? It takes the reciprocal. So I have 1/2 now to the x. So I'm going to put a little star here. You have to rewrite it. Whenever you have some kind of negative exponent, we recommend that you rewrite it. Otherwise, you won't see it right away. But now when I look at it, am I going to have growth or decay with this 1/2? I'm going to have decay. Very good, because it's between 0 and 1. And again, you don't have to write that every single time, but just for the sake of notes, when you guys are going back to check on it, you know why we wrote decay. Now this one's a little tricky. Before we even look at the exponent, what's 0.25 as a fraction? 1/4. So I'm just going to rewrite it as 1/4. And now we look at this negative and say, what happens? What happens to the base? Yeah, it's going to flip on us. Again, being able to realize that is a huge and essential math skill. We're working with exponents. So we have 4 to the x power, so now I can look at my base. Not until I highlight that piece are we really looking at the base. So are we growing or decaying? We are growing. Very good. Okay, so take a second, please, with your group or yourself, and read problem 2 and see if you can answer the following question. Explain why Scott's reasoning is incorrect. And then, so try 4 and 5 with a group. If you don't have a group member, feel free to join someone, or you can still work alone. That's fine. Okay, so you're reading Sarah and Scott's either with your group or alone, and then you're going to answer 4 and 5.
Well, it just says why Scott is incorrect.
Oh, shoot. I don't read the book.
It happens.
That kind of has a deeper down to it.
That's okay.
That isn't nice. We'll just mess it up.
Man, you're acting like you're acting on Friday.
No, Scott.
Nah, he's too.
You seem really focused on your
I'm too.
adding lead.
Make sure you're here.
I will be here today after school instead of Thursday. I will be here today after school instead of Thursday.
I just want to see what you say.
I'll be at kitchen table if anyone wants to come by there.
The kitchen table.
I will not be here.
We got like kitchen appliance.
Yeah, they got food. They got everything in the night.
But they give you
They have
crackers.
snacks, yes.
And they got help. Like,
Not only Spanish, but English too.
oh, that's a good. What's a good way to hear?
English. We're reading The Great Gatsby.
I hate English.
But I can't believe like Gatsby dies at the end. Like that's just gonna. That ruined the book. Yeah.
All right. So let's talk about this. It says, when Scott here, he says, for exponential growth functions, b is greater than 1. For exponential decay functions, b is less than 1. Why is he incorrect? Yeah, so we forgot to make sure that he's excluding those negative values. So this piece right here is why he's incorrect. It has to be between 0 and 1. You can't have negative as your base, because you would be neither growing or decaying in that situation. Okay, so again, b cannot be 0 and it can't be negative. That might be something just to mark off. B, the base, cannot equal 0 or be negative. Just something kind of to mark for yourself. And it says Sandra, another student in the class, said if the base is a fraction, the function is an exponential decay. Is Sandra correct? Is Sandra correct?
No, because a fraction can still be like bigger than like the one that's still.
Yeah, we kind of already witnessed that. So no. We can have what's called an improper fraction, which I know that you guys might have not heard that in a while. And that's when we have something like we already talked about. Here's an example. We already talked about that 4/3 to the x power. Okay, the 4 is bigger than the 3. That's a situation where a fraction would be growing. Okay, flip the page when you're ready. Gatsby.
Oh my
It's a good book. Well, I think everyone reads Great Gatsby in high school, yeah. He's all upset. I love it. All right. So, for each exponential function, complete the following. Fill the table of values. So, I'm really going to challenge you today because I'm not going to let you use a calculator. Because we want to practice just trying this out. I promise you can do it. Okay, maybe not the very first one, but the other ones you for sure can. So, when we plug in this -4, 3 to the -4, what is 3? So again, try to manipulate your brain for a second. Pretend this negative is not here. What's 3 to the 4? 3 times 3 is, and then times 3 again, times 3 one more time. 27 times 3 is the only one that you really have to kind of think about.
That's like 90 something.
It's close.
87.
Close.
You guys can think about it.
81. Very good.
You guys can also manipulate a little bit in your head. You know you're gonna have 4 3s, right?
It would just be 9 times 9.
It would be 9 times 9 because these ones are 9. These
Yeah.
can make 9. You get 9 times 9, and we all know what 9 squared is, right?
81. It's a good way to look at it. So now that we have this negative, though, we don't have 81. We have what? 1 over 81. Very good. Okay, that one was the only really one I think that was challenging. The rest of them are pretty straightforward. Because we know 3 to the -3. Well, what's 3 cubed?
27.
27. Well, we know the negative does what? Flips it. So I have 1 over 27. Okay, finish the rest of that table. You got this. And pop the boys. Make you do a lot of work right now.
Oh yeah, we're not using calculators.
Yeah, no calculator.
Wait,
Silly.
how'd you figure it out?
I wrote it up there.
Bro, 3 times 3 is what?
9.
24 times 3 one more time.
27.
Oh, you're talking about the next one. Sorry.
I'm talking about this.
This one?
Not this.
This one?
Yeah.
So 3 times 3 times 3 times 3 is really 9 times 9.
Oh, 80.
81. So that one was the only that hard one. But here, 3 times 3 is 9 times 3 is 27. And that negative means that we're flipping it to the bottom. That's all it means. That's why we have 1 over 27. Okay, and so the same thing with 3 times 3.
We think the same thing.
9.
Nice. So instead of 9, I have what? Is that negative? Not negative 9. The negative is the exponent that flips it to the bottom. So I have 1 over 9. Same value, yep, it's all over. Yeah, there you go. So whenever you have a negative exponent, it flips it to the denominator or vice versa. Good. Good, you guys did awesome. See, you're getting a lot better. The more you practice, the better you get at it. So this one was 1 over 9. This one was 1 over 3. Anything to the 0 power is 1. Then look, this is pretty easy because it just flips. Now we no longer have a negative in the exponent. So this becomes 3, then 9, then 27, then 81. Okay? So you're getting better at it already, so please plot those points. Try your best to estimate. Obviously, 1 over 81 is very close to 0. So I'm just going to go ahead and go 1, 2, 3 and be like right close to it. And then I have 1, 2, and it's like a little bit higher, a little bit higher. Then we get to 1. That's an important point. Then I have 1, 1, 2, 3. And then I have 1, 2, 3, 4, 5, 6 here. And that's going to keep going. Somewhere around there, and that's all we really need. You don't have to keep plotting it. But so I have this graph that looks like this here in black. So as you can see, and whenever you're reading a graph, just like you're reading a book, you read left to right majority of the time, especially when we're talking about domain. When we're going left to right, it's shooting up. Do you think that's growth or decay? Growth. Okay, we have growth here. All right, again, going to challenge you here. It shouldn't be that challenging because you already have all of the powers, but now it's a little different. See if you can do this. Take a second, take a minute. You have all those powers already, just be careful because now you have a negative exponent. See if you can apply that to all of these.
Is that negative times negative is positive? So we just see it. So the first one was 81.
Just 81.
Explain it to them.
Why? How come this is 81 instead of 1 over 81 like this one? It's negative, that's what, with the negative times negative.
Bro, why don't I just
Oh,
say it
yeah.
right loud,
It's
bro?
positive, so now all these negatives are
So
going to
3 was the 4th power is what? You figured that one out.
I know the first.
I am so blessed with the best teachers.
It's not because now we have negative,
Best
right?
partner. Oh.
Oh, yeah, am partner. Best partner.
So now it's
Well,
you're
I mean, they could be your
finding the
teachers
radius.
too, if they teach you something
A little
new.
different. So my first question is, what's 3 to the 4th power? We already figured it out, right?
See, yeah, have you guys been listening to that?
Did we figure out 3 to the 4th already? It's 81. Okay. So
I would power those
when I
things.
put in 3 to the negative 4th, what matches the sign?
No, not part. It doesn't have to be.
So there's only so like
Squats.
a negative times a negative is 8. So what's 3 to the 4th?
How much did you pay?
Yeah. So again, when you're multiplying a negative times a negative, you should be getting a positive. So those first ones, you should not have fractions. If you do, look at them again. Look at that, you guys are getting better. Check your answers. I walked around. As I walked around, I started seeing some negative answers. Can we produce negative numbers in exponential functions? No. Okay, so always check your work.
Since we have all these points here that we can plot, we don't need to plot this one.
When you're done and when you're done only, you can take a look up.
But we don't need to worry about that.
If my pen will work. And then 1 over 3, 1 over 9. Okay, so same kind of points here, but now you can see everything's flipped. So go ahead and plot those points out. All right, then we got
Oh, so those two.
I'm just gonna sketch this one. I'm not really too concerned. Okay. So in this situation, again, you're reading left to right. So I'm gonna go to my leftmost point, which is this arrow over here, and so you can see, is it growing or decaying? Decaying. It's shooting down. Okay, so we're decaying. Cool. All right, it says compare the two graphs. What does a negative on the exponent do to the graph? Now, not the base. We're not talking about the base anymore. We're talking about just the graphs. So when you compare these two, one had a positive exponent and one had a negative. It reflected over what axis? The y. Awesome. That was great. Reflect over the y-axis. Because we're leading into transformations here. Kind of exploring why that is the way it is. Okay, notice on number 6, as the x values get smaller, and on number 7, the values get larger, both graphs get closer to the x-axis but never touch it. What does that mean? Try to go back, way back to like chapter 9 where we like had these weird things. What'd you say? Yeah, it has a horizontal asymptote. Awesome. Okay, so it has a horizontal. We're bringing it back. Asymptote. It's a weird spelling. Asymptote. Asymptote. Okay, at what? Y equals what number? Yeah, 0. Very good. I'm going to show you that here in a second. Okay, so again, with my highlighter, I'm just going to highlight one piece. That y equals 0 is going to be that asymptote, so that when you go back in your notes, you know why that is the way it is, because you can correlate it with that color. Okay, so again, it slowly approaches that axis, but never touches it. Now, if we were transforming it, like if I put, it went down 2, then that all would shift down, including the asymptote, and that's when we can have negatives, but that's only when we're talking about transformations. So let's talk about both of these. Again, we have growth and we have decay. What is the domain of both of these functions? All real numbers, which is negative infinity to positive. Because it goes forever left and it goes forever right. However, it does not go forever up and it does not go forever down. What is the range of both of these because they have this asymptote at the same place? 0 to where? Infinity. Very good. Do we include 0? No. Very good, because I have an asymptote there. I can't. And we know that exponential functions are not going to produce 0 or negative numbers if it's not transformed. Okay. We already talked about the asymptote. Where is it? Y equals 0. And I'm just going to kind of label this as my horizontal asymptote so you know and get used to those words again. Kind of like ha, but horizontal asymptote. Okay? We had vertical in the past. We don't have vertical now. It's usually only when we have rationals. All right. Intercepts. We have a y-intercept at both of them. Where are they? Where does it cross the y-axis on both? 0. Very good. So I have 0, 1. Did you say 0? Yeah. I meant 1. Sorry, guys. Now, this, we're bringing it back. I know that you guys weren't the biggest fans of these, but we're going to try it again, especially if you're going to calculus eventually in the future. You need to know your limit statements. So here's what I like to do when I do limit statements. I like to write them out first before I even try to mess with them. So I'm going to go ahead and write it out. I have the limit as x approaches the left side of the graph, which is infinity, negative infinity, right? The left side. Where does the function go? Again, I'm not going to answer it yet. I'm going to leave that blank. Then I'm going to set up the other one. The limit as x goes to the right side of the graph, which is infinity. Where does the function go? We're going to fill in those answers here in a second. I might as well just go ahead and fill it in for the other side too, just to get ready. The limit as x approaches the left side, which is that negative side. Where does the function go? Trying to get you, I'm going to keep saying it so that you get used to the words. The limit as x approaches the right side, which is positive, where is the function going? Okay, then we're going to fill in those blanks. Sometimes the hardest part is just writing those out because you forget how to do the notation. So here we go. Come back to me. Come back. Okay. Let's start with this one. As x, here's x. I'm x. I'm a walking person on this little sidewalk here. As x is approaching negative infinity, where is the function approaching? What did you say? Think y value. Where is it approaching, but never touching?
0.
0. Very good. So 0 goes here. And then I am x and I'm going to the right. Now, where is the function going? Infinity. Very good. The y values are going positive. Now, that makes sense because you're growing. You're starting at 0 and you're shooting up to infinity. Sorry, my hands get crazy in Italian, so it happens. All right, so other side now. I'm x and I'm going towards negative infinity. Where is the function going? To infinity. And the reverse. I'm x and I'm going towards positive. The function is going towards 0. And if you remember this from chapter 9, we talked about that. Your asymptotic behavior is going to approach your horizontal asymptote if you have one. And the very last piece, the left graph here, the growing one, am I always growing, increasing, or always decaying if I am in exponential growth? Am I going to be increasing or decreasing? Yeah, I'm going to be increasing. And it's always, so from negative infinity to positive. So intervals mean those parentheses. Give me an interval. Now the decaying, is that going to be increasing or decreasing always? Decreasing. Good. And that wraps up today. Yep, so you have 15 minutes. Okay, to work on, 12 minutes to work on your homework. You should be able to walk out with it done. I will print a key for you to look at. Again, try your hardest to do them without a calculator. There are some of them that are very difficult that we would not recommend you without using a calculator. No, you're right. No, I'm just reading it. You pick out ones that like would. Okay, what about the front? Oh, it's growing or decaying. Got it. Yeah, you should be able to do this whole thing without a calculator. You can check your answers with it. Again, you're not going to require you to not have. I actually don't really know about that in the test, but we have to.
There's gonna be a non-calculator portion.
Okay. So, recommend trying it first, and if you get stuck, that's when you go to your calculator. That's how you should be a good mathematician. First try it, and if you get stuck, then rely on technology.
Wait, what is this? Well, this is.
What is your y-intercept?
Yeah.
What is always the y-intercept if they're not moving up, down, left, or right? Just 0? Well, it's not 0 comma left. Okay, so if you notice here in our graph, some of you are asking about the y-intercept. Both of them are at 0, 1. It will always be at 0, 1 unless you transform it. So for example, there's one that has a 5 in front. So instead of having 0, 1, I would have 0. So I have 0, 1 always unless it's transformed. If I put a 5 in front of my function, like number 4 on your homework, instead of having 0, comma 1, if I'm stretching by 5, I have 0, comma what?
So guys, your y-intercept is always going to be when your x value is 0, because that's where it's going to cross the y-axis. So you have to think, okay, well, what is the a value in front? The a value would be your y-intercept.
Oh.
There you go.
Yeah, 0, comma 1. Because there's no like coefficient in front of the a. So it'd be the same as these two.
I like these conversations I'm hearing.
Because here, look, did you not see the mark? Because this would be 0. No, for like the growth or decay. There's a negative exponent.
Okay, so,
Yeah, but he's not.
yes, because this is less than.
I'm gonna see if I'm right, but it's like
It's gonna be great.
well, I mean, a fraction, it could be an improper fraction. So then I don't like this. Like I want to be able to write it out. I know what you're trying to say, but like
I gotta print it.
write it as like a
Oh, yeah, yeah, because it's not bigger than the denominator. Number 5 is the big. Sure. Is it just, do you ever want to